Sorry, I'm going to explain the internal pull-up resistor. So the internal pull, I'm going to explain and why. Because I think earlier in the notes they say that the only way if the pin is not in use, we default it to one input so that we can use less power. And let me explain why how the logic of less power works, and then I explain floating before you go into the internal polar resistor. So now, assuming this thing is set to an output, but it's idle, it's not doing anything. Now, if we set an output, meaning this would be closed, right? Would have fed a one from the DDR, if you remember. A one would be here. That means it would be closed. So if it's closed, that means current is flowing from here to this pin because you want to read whatever is here to this pin and bits travel with current, right? I remember from our physics back then, if like let me say I have an open wire that's just there and it's carrying current, that means energy is lost in form of heat, if you remember that. So that means if this is just open, it's just bare, energy will be lost as heat. And that will happen quickly because like the physics, because yeah, it's colder, so that means heat is being lost quickly. So if it is being lost quickly, that means the 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 rate of losing heat is faster. You know, there's other things which I don't want to go into, but just know, yeah, current will be lost, power will be lost in form of heat, which will be wasting our microcontroller's energy. Because imagine that your microcontroller is relying on, let me say, dry cells. That means if you're wasting power here in form of heat, then that's not very economical. So that's why they default it to be an input. Because when it's an input, you feed obviously a zero here, you'd open this circuit. That's the only way you can set it as an input. You'll have to default here to you have to open this circuit. The only way you open this circuit it's by feeding a zero in the DDR. So this will be open. So for that matter, a condition called floating will occur. A condition. So floating is that condition you've set it to want to be an input, but nothing is coming in. And I think they said one floating happens, and it interrupts might happen or what, because Simba is set to an input, but it doesn't know what to expect because nothing is coming. It doesn't know if it's a one or a zero, or maybe external conditions may cause a one, and that one may be radial, which will maybe cause errors in your code. So that condition of uncertainty at the pin is called floating. So now we want to we want to we want to put a definite value at this register. Remember this register down here, this register down here reads whatever is coming in here. But now we have a condition of floating. We don't know what to expect. Like anything could maybe come in because of external. So yeah, floating will be maybe would cause unnecessary and unstable values that if maybe some external features because maybe a one was and maybe that one here would affect your code in some way. So you don't want that uncertainty. So now here that's where the internal pull-up resistor comes. It's supposed to pull, like supposed to make here a one be ready to this, a constant one to be ready here. Like to form, let me set to a definite value, one here in this D flip flow. So avoid that uncertainty. So what happened? It's called anti pull up resistor because there's a resistor here. And because now they put a resistor here so that weak current could flow. Remember, you want from that, is it that from the okay, the VIR thing? A high resistance would mean a weak current flowing here. So in case there is no current flowing from this side, you'll be able to read this current that is weak into here, and that current which is weak will be reading a one here, right? But in case an outside current comes, let me say an external device is inputting that, of course that current will be stronger. Because there's no resistor here, so that means that current will, should I say, overpower this weak current and override whatever is being read by this pull up resistor, to override whatever is being read by this pull up resistor, and then we'll be able to read the input. So that means this internal pull up resistor current, the current from up here, will only be significant here, will only be significant within this D latch if nothing is coming here, because for it it's weak. It's weak because there's a resistor here, and the resistor is usually a high resistance to make the current weak. So that means it will only be dominant, not to be able to influence whatever is in this D latch here, if and only if no input is coming at this pin. Now that's the importance of the resistor, this resistor here. So now we have to cater for the logic of how we actually make a 1B read up here. Like how we actually set a 1 how we actually set our current to be able to carry a 1 to our D latch down here. So now this is where we come to this side. So now in the earlier notes they said for that to happen, first, let me first do something. So basically, the first thing we want to do is open this circuit, right? That we know, we want to open this circuit. And then we can open that circuit is by writing a 0. So there's a 0 here. So this circuit is open. But then we have a component here. This is an AND gate, right? This is an AND gate. And remember, for an AND gate, for us to remember, as you can see, this AND gate is connected to the polar, to this resistor here, right? This resistor here. That means whatever result comes out from the AND gate is what will be stored here. So we have a 0 here. So, and I said whatever this AND gate results into is what will be stored here in this deep flip flow. So that means we want to set a 1 here. Remember, for an AND gate, the only way we can have a 1 is if we have a 1 and 1. A 0 and 1 yields a 0 in an AND gate. If you use a 0, 0, 0 yields a 0. But we want to have a 1 here and this AND gate. So that means that, so in the earlier notes, they say you default a 1 here. So when you default a 1 here, like write a 1 here, you can see from our circuit here is connected to here, and here is connected to our AND gate here. You can see that part here. From here to here. And of course, this is just for reading. Like I said, this line is just for helping the litmus test for our CPU. So that means whatever is being read here will come, obviously, current can travel in either direction. Electricity works here for the PC to also read, then also some will go this side and it enters our AND gate. So that means we also want another 1. So now I want to yield a 1 here. That means we also want to have a 1, another 1 here. But remember our deep flip flow here, that the other deep flip flow that's storing, the other register actually has data that we can use is storing as 0, and yet we want a 1 here. So that means from using the same logic, current flows from here. Remember, we want it to flow into our AND gate, but then it's a 0. So here we put a NOT gate. So now that NOT gate makes our 0 to become a 1. So by the time it comes here, it's a 1. So that means we have a 1 here and a 1 here. And when you add a 1 and a 1, you get a 1 here. So that means there's a 1 here. That means our current here will come down and be a 1 here. So yeah, so basically I think that's the basic logic of how the internal polar resistor works. So I think I'm going to go to the next bit, which is multiplexing, pin maxing. And I'm going to explain pin maxing. So from the notes earlier, they said that pin maxing, let me say, remember on the Atmega, you have very few, you have few ports. You have C, D, and B, I think. Yeah, there are three. But you could have a complex system. Let me say you want to have like a very complex system where you need very many ports. But that a microcontroller only has three ports. That means let me put get a so you have one pin, but you could have a very complex system that requires your system requires a lot of ports and pins. So in that case, you want to utilize the few pins you have for different purposes. So remember, I think up in the notes, they say that for such a condition, in case you have a very complex system, you may need a very bulky system in case you want to just be using one pin for only a particular role. But then pin maxing is where one pin can do can do two things at a time. Like let me say, one pin can be part of, let me say, two different systems that but at the same time. Of course, you define that in your code. Like your system can be able to service two systems at the same time. So in this case, you can see you have another system called the peripheral, and then you also a peripheral, of course, an external device. Then what could be an external device or anything else. But just not peripheral is another system. Then you also have a system from the microcontroller here from the FVR CPU. So both of these systems want to control this one pin. So now hence you need pin maxing. Yeah, so basically you have two systems. So now we want these systems, it will be this one pin to be able to service both the two systems I'm talking about. So here we have these are they multiplexers, multipliers? I'm not sure of the name, but I think it's multiplexers. Yeah, that's the name. So now our multiplexers, remember from a multiplexer also takes in three inputs. Input one, two, and three. Now our multiplexer has two inputs and then one control line. So I'm going to remind you of how they work, how a multiplexer works. Now remember, a multiplexer could either be to one. That means a multiplexer has one control line and two inputs. So here we have one control line, which is our three here, and then two inputs. So now, if I let me draw a table, let me say the so this is the control line. Let me call it P. So from our architecture, this is 0, 1, 0, 1. So this is 0, 0, 1, 1. Wait, I think our table continues with 0, 1. Wait, I think this is the wrong table. This has to be a 0, it has to be a 1, 1. This has to be 0, 0, 0, 4. Wait, yeah, so I've fixed the table, but I think I've drawn a wrong table at first. So now our control line. Now we are supposed to have, remember, we are supposed to have an output. So let me uh, put our output here. Out. So now our multiplexer works like if our control line, you could maybe say whenever it's a 0, read A. When it's a 1, read B. That means if our control line B is reading as 0, that means you only output whatever A has. So in this case, our control line is outputting has a 0. That means you output whatever A has. So it will be 0. Then you also continue our control line as a 0. So it will be a 0. Then you also continue our control line as a 0. So we output our A as a 1. So write a 1 here. This is a 0. Our control line still has a 0. Our A is a 1, so we put a 1. So then when our control line has a 1, we read whatever B is outputting. So our B has a 0. So read a 0. Our control line is still a 1, so we read a B. Whatever B is outputting. Our control line is still a 1 to output whatever B is outputting, which is a 0. Our control line is still 1, so we output whatever B is outputting, which is a 1. So now that's how a multiplexer works. So now in this case, that's what you can see we have 0 and 1. So in case our control line here, the one from down here is a what? Is a control line. So that means if our control line has a 0, we'll read this line. If our control line has a 1, we'll read this line. That's why there are zeros and ones written there. So now, in this case, obviously, the earlier notes, remember here, if you read the earlier notes concerning this diagram, they say that, like in reality, our pins, we usually work with 8 pins, right? The pins are 8 usually. So that means that an HDD latch stores only 1 bit. So for you to have that effect of 8 pins, you would actually have to have 8 latches from index 0 to 7, 0 to 7. So that's what they're trying to show you, that in reality there are actually 8 of them, but in the earlier diagrams they're just dealing with one to for us to get the interpretation. But in reality there's supposed to be 8D latches, 8D latches, both for this is for the data register and this is for the DDR, and these ones all correspond to a pin. They all correspond to a pin. Both of these both correspond to a pin. Each setup here corresponds to a particular pin. Yeah, so that means in reality you would have another system, a similar system like this from this DDR to another DDR here to form a similar system, but that will be hard to represent. So they are giving us a block view. So in this case, we want to provide a system that controls the use of this port pin. So in this case, assuming now the CPU wants to use a system, right? The CPU is a system that wants to use the pin. So it doesn't matter whether it's input or output. Of course, I already told you the basics of input and output. So now, in case it's the CPU that wants to use the system, that means your code will instruct the peripheral, because you can see our control lines for the multipliers come from the peripheral, right? So you write your code in a way that instructs our peripheral to output a 0 here. So if it's a 0 here, that means we'll select this DDR. I remember this DDR is coming from the CPU. I remember this DDR maybe the CPU wants to use this as an input or output. Doesn't matter. But all we know it's the CPU controlling this pin now, because now the DDR that's allowed to flow. Now maybe the DDR may set this to one input by maybe writing a 0. So then maybe the DDR wants to set this to one output. So if it's an output, maybe it has written a 1 here. But then for an output, that has to flow from these registers here. But then you can see there's a multiplexer here. And remember, now that multiplexer, we again have to write our code now to allow our a 1 to be a 0 to be written here. When a 0 is written on this control line, remember the control line will instruct the multiplicator to only output whatever is coming from this line. This line is controlled by the CPU. So that means what if we had put whatever is from this side, that means whatever is here is what is here because a 0 is coming here. So that means data will be able to flow to this pin in case the CPU wants to set it as an output. So, but in case the peripheral wants to use this peripheral wants to use this pin, so it will just have to write a 1 here. Remember, 1 here selects this thing, and this thing may comes from the what from the peripheral. You can see this line here comes from the peripheral, right? Then maybe it also wants to set it maybe to an input or output, doesn't matter. Now that line coming from the peripheral. Then also here, maybe the peripheral also wants to block off the CPU completely. You can see it will also have to write a 1 here. So that means if there's a 1 here, whatever is here will be output on this line. So hence the peripheral is in control because you can see this line also comes from the peripheral. So that's basically how pin maxing works. It basically just deals with these multipliers or multiplexers. I'm still not sure of the name, but yeah, just deals with both of these. Both of these help the pin either to be used by the CPU or the microcontroller and the peripheral. So two systems can be using the same pin. So yeah, thank you. I think let me see what other diagram is there. Let me look through. So now the next diagram is in timer bots, and this is first. I'm going to explain pulse width modulation. Now, pulse width modulation, we have two graphs. We have two graphs here. There's first pulse width modulation and the phase correct pulse width modulation. So I'm been doing. I'm going to just explain the diagram. Then we'll just verify with with the notes above. So now in this case, now pulse width modulation is a way of converting analog signals to digital signals. Remember, in our microcontroller, we are only dealing with registers, but we want to output a certain signal. At an analog signal, we want to get it and find out what in outputting it. But here we are dealing with registers. So here they have given us a max. Okay, they have given us two reference. Let me say A and B, and let me remember these are registers. So let me say these A and B store the value. Like let me say we are trying. Let me give it some context. Like let me have a temperature sensor. And a temperature sensor we take readings at certain intervals. Now when we take readings, uh, the readings are let me say stored in. We have two registers of A and B. These are compare registers with the output compare register. So these ones two are like A and B. Because remember, when a temperature sensor gives out, let me say when it's sensing, how the sensors work is like a certain voltage is generated on the sensor. That voltage flows into the processor, and then maybe the value a value is stored in either A or B or whatever. But all you have to know that A and B are our reference, our reference, our reference voltages that you want to generate, A and B. Of course, the registers and the values are stored there. So now we have what we call a counter. Now a counter is a counting register. Okay, I think it's a TCCNT. timer counter control register. I think sound we use here, you verify with the net. So now it keeps updating its value from 0 to 255. Like remember, counter our registers are usually 8 bits, right? So that means it keeps, and now the maximum of the 8 bits is 255. That means it's going to count from 0 to 255. That's why it's going to count, because the 8 registers. So it keeps increasing its value from 0 till 255. So now notice here it started with OCA. So when it reaches OCA, so here we are plotting a corresponding graph. Like when it starts when it's high. Like I think there are two modes, like inverting and non-inverting mode. Non-inverting is where the CPU starts on when it's set on a 1, then when a change occurs, it sets to a 0. Then it starts when it's on a 1, it sets to a 0. So in this case, when you look at OCA, so as the counter counts, remember when it starts, you can see here corresponds to here. When the counting starts, it's high, it's set to a 1. So now at that point where the value of our counting register is equal to OCA, at that point, you can see this point corresponds to this point. A toggle happen. A toggle is what is a situation where you get the opposite. You get the opposite of what's happening. So let me say if you are set to a 1, set to a 0. So at that point, it will set to a 0. So that's why it goes down. Now, here, when our counter reaches 255, it switches over. Okay, should I say it just switches off and goes back to count again from the start? So when it goes back to count again from the start, remember it starts when it's high on a 1. So again, it's high on a 1. Now it encounters this point where they are equal. It will again toggle and say until it climbs up to the top here and again falls down and starts again. When it starts again, you realize here at this point where it toggles, it corresponds to this point. Then again, it will flip over, and that process continues on and on. Now, that is for OCA. That's what happens for the first pulse width modulation, because this is first pulse width modulation. In first pulse width modulation, when you reach the top, the counter just goes off and decides to count from 0 upward again. That's how the pulse width modulation works. Well, we look at the phase correct later. So if you look at B also does the same thing. It starts when it's high. Now at that point where they are equal, it toggles. It toggles again until we start again. When we start again, we are again on a high. Here we are again set to a it's set. You can see at the point where they are equal, it toggles. So that's the process that keeps happening for the first pulse width modulation. Then we come to the phase correct. Now, in the phase correct, what happens is here. Remember, in the first year, when it reaches 255, it just folds. Or should I say that the counter just switches off and starts again? That sort of thing. But in the phase correct, our counter counts up. Let me say 255, then it also counts down. So that means it's wider, because for it's like it makes two journeys: the journey of going up and then counting down. Whereas the phase correct, it just goes high and then switches off and resets. Should I call it resets? But here you have to count up to 255, then you count down to 254, 253, 252 till you reach 0 again. So that's basically what happens. So now let me begin from this section here. So now assuming it started from a 0, it's counting up. Now when it counts up, remember it starts when it's set, right? Because this is a non-inverting mode. Now when it's set, because you're looking at OCA, this is the two, this is looking at OCA. Now when it encounters that point where they are equal, it will toggle and go low. It will keep low until that point. Like here it's low, it's low here. until that point, in the counting down where the equal again, because remember we reach a point and start counting down. So that means we are bound to find the value that equal again a second time. So again at that point where the equal again, it toggles and changes form. It toggles and changes form. So again it has reached zero. Now remember when it reaches zero, it counts starting from a high. So it will just continue on starting when it's set until that point where they are equal here, here they are equal, then it will change. And that will continue going on. So let's also look at OCB. Now OCB, it also starts when it's set. And now at that point where they are equal, it will toggle and go to a toggling just means going to the opposite state, like I said. So it will toggle and go down and wait for that point when they are equal again. Here, when they coincide again, then again here, then it will toggle and go to be set on a high. But remember, it will hit at zero. It has to restart again. But remember, when it restarts from a high. So it will restart on a high, till again it reaches this point. Then again it will toggle. When it reaches this point, it will again toggle. That's basically how they work. So the difference between first first pulse first pulse width modulation and phase correct is the fact that both of these are in the first width in the first pulse width modulation we count till the top, but we don't count downwards. In the phase correct, we count till the top and count downwards. So basically that's the difference. Yeah, I think I've explained the diagrams unless you want more of or any other diagram to clarify.